Uniform acceleration. A body is said to possess uniform acceleration if the velocity of the body increases at a constant rate or decreases at a constant rate throughout its motion. Suppose the velocity increases at 5 meters per second. At starting time it's 0, after 1 second 5 meters per second, after 2 seconds 10 meters per second, after 3 seconds 15 meters per second. Like this it increases constantly. Then we say it has got constant acceleration. Similarly, if the velocity decreases at a constant rate, then also we say the body possesses constant uniform acceleration. Actually, it is uniform retardation. By the definition of uniform acceleration, we can derive the relation v is equal to u plus at. We know a is equal to v2 minus v1 by t2 minus t1. A is equal to v2 minus v1 by t2 minus t1. Let us assume t2 minus t1 as the time taken and indicate it with t. T2 minus t1 is the time taken. Let us indicate this time taken by small t. Then a will be equal to v2 minus v1 by t. A is equal to v2 minus v1 by t. On rearranging, we will get v2 is equal to v1 plus at. Vt is equal to v1 plus at. v1 is the initial velocity. Generally, we represent this initial velocity with the symbol u. Hence, we will get the relation and the final velocity will be represented by v. So, v2 will be replaced with v and v1 with u. Hence, the relation becomes v is equal to u plus at. v is equal to u plus at. Now, let us take velocity time graph of an accelerated particle. Here, the initial velocity of the particle is u and the final velocity is v and the time interval is t. This motion is represented by the blue line. Now, the horizontal dotted line drawn against u that indicates the initial velocity from O to u is initial velocity. It is indicated by u on the right side. And above that line there is at, which indicates the change in velocity. In t time, the change in velocity is at, where a is acceleration. So, the total final velocity v will be equal to initial velocity u plus the change in velocity at. So, we will get the relation v is equal to u plus at. We can derive the relation v is equal to u plus at from this graph. Derivation of the relation s is equal to ut plus half at square from graph. Derivation of s is equal to ut plus half at square from vt graph, velocity time graph. Let us take the same graph which we have used for deriving v is equal to u plus at. In this, we know the area represents displacement. So, the displacement in t time is x-axis and x-axis, the abscissa is t and y-axis it is u. Up to u, the displacement is the area of the rectangle, which is ut. Above that rectangle there is a triangle, right angle triangle. The area of the right angle triangle is half at square. A is acceleration and at is change in velocity. At is change in velocity. So, the ordinate becomes at and the time axis becomes t. So, half into at into t, that becomes half at square. So, the area of the triangle is half at square and the area of the rectangle is ut. So, the total displacement is s is equal to ut plus half at square. Like this, we derive the relation s is equal to ut plus half at square using this graph. Derivation of the relation s is equal to ut plus half at square from principles. Let us consider a body whose initial velocity is u and its velocity becomes v after a time t, having an acceleration a, and its displacement is say s. Then its average velocity is v plus u by 2. Average velocity is initial velocity plus final velocity by 2, v plus u by 2. Displacement is average velocity into time. Average velocity into time gives displacement. So, v plus u by 2 into t gives displacement. So, we will get the relation S is equal to v plus u by 2 into t. This is relation 1. We have already derived the relation of final velocity v is equal to u plus at. V is equal to u plus at. This is equation 2. Using these two equations, we derive the relation S is equal to ut plus half at square. We have the relation for displacement S is equal to u plus v by 2 into t. U plus v by 2 into t, but v is equal to u plus at. So, substituting u plus at, we will get u plus at plus u by 2 into t, or S is equal to 2u plus at by 2 into t, or that is ut plus half at square. Therefore, S is equal to ut plus half at square. Like this, we derive the relation S is equal to ut plus half at square. Difference between position and displacement. We have the relation S is equal to ut plus half at square. Here S is displacement. But displacement is change in position delta x. S is equal to delta x. Delta x is change in position. Change in position is final position minus initial position. Xf represents final position, xi represents initial position. So, it is xf minus xi. So, from this, final position is equal to xf is equal to initial position plus displacement. Xf is equal to xi plus s. For s, let us write ut plus half at square. So, the final position xf is equal to xi plus s, that is equal to xi plus ut plus half at square. Like this, we find the position. Derivation of the relation v square minus u square is equal to 2as. Derivation of the relation v square minus u square is equal to 2as. We have displacement is equal to average velocity into time, which can be written in the equation form, in the form of equation as S is equal to v plus u by 2 into t. This is equation 1. From the relation v is equal to u plus at, the relation for time is written as t is equal to v minus u by a. V minus u by a. Substituting the value of t in 1, we get S is equal to v plus u by 2 into t. For t, write v minus u by a. So, we will get S is equal to v plus u by 2 into v minus u by a, which becomes S is equal to v square minus u square by 2a, from which we will get v square minus u square is equal to 2as. Like this, we derive the relation v square minus u square is equal to 2as. Displacement in the nth second. Displacement in the nth second. To have a concept of this displacement, let us see the figure. Here I have drawn 3 arrows. The first one is S1, that is the displacement in n seconds. The displacement in n seconds. Underneath it there is S2, which gives the displacement in n minus 1 seconds. S1 is displacement in n seconds and S2 is displacement in n minus 1 second. And the remaining part, that is shown by small arrow, that is the difference, that is Sn. Sn is the difference of the two vectors S1 and S2. This Sn is equal to S1 minus S2. The difference of S1 and S2 gives Sn. So, this is the relation which we are going to use for finding the relation for Sn. We know that S is equal to ut plus half at square. If you take t as n, we will get S1 is equal to un plus half an square. For t, if we write n, we will get S1 is equal to un plus half an square. For t, if you take n minus 1, then the relation becomes S2 is equal to u into n minus 1 plus half a into n minus 1 whole square. S2 is equal to u into n minus 1 plus half a n minus 1 whole square. So, by taking these three relations, Sn is equal to S1 minus S2, S1 is equal to un plus half an square, and S2 is equal to u into n minus 1 plus half a into n minus 1 whole square. We are going to derive the relation for Sn. Sn is equal to S1 minus S2. So S1 minus S2 is equal to un plus half an square, un plus half an square minus half u into n minus 1 plus half a into n minus 1 whole square. S1 minus S2 is equal to un plus half an square minus half u into n minus 1 plus half a into n minus 1 whole square. Let us simplify this. S1 minus S2 is equal to un plus half an square minus half un minus u plus half a into n square minus 2n plus 1, which on simplification becomes half an square minus an plus half a. U into n minus 1 plus half a into n minus 1 whole square becomes un minus u plus half an square minus an plus half a. Now let us multiply these terms with negative sign, then we will get S1 minus S2 is equal to un plus half an square minus un plus u minus half an square plus an minus half a. Next, let us simplify this further. Un minus un gets cancelled, plus half an square minus half an square gets cancelled, plus half an square and minus half an square gets cancelled. So we will be left with u plus an minus half a. U plus an minus half a. This is Sn. Let us take a common. Then the relation becomes u plus a into n minus half. U plus a into n minus half. This is the relation for Sn. So Sn is equal to u plus a into n minus half. Now let us write the four equations of motion which we have derived. First one is v is equal to u plus at. Second one is s is equal to ut plus half at square. Third one is v square minus u square is equal to 2as. And the fourth one is Sn is equal to u plus a into n minus half. These are the equations of motion in kinematics. Let us recall the physical quantities involved in kinematics. Initial velocity u bar, acceleration a, time interval t, final velocity v, acceleration a, and starting point is O, displacement s, and the final position is a, and the displacement in the nth second is Sn. These are the physical quantities involved in kinematics. Now let us write the four equations of motion which we have derived. First one is v is equal to u plus at. Second one is s is equal to ut plus half at square. Third one is v square minus u square is equal to 2as. And the fourth one is Sn is equal to u plus a into n minus half. These are the equations of motion in kinematics.